In MATLAB, there are built-in functions for numerical differentiation and regular differentiation as well, and especially for the numerical differentiation. These functions can be generally used. Del2 use discrete Laplacian. We are not using this too much, but diff function uses differences and approximate derivatives. Gradient uses numerical gradient. Polyder uses polynomial derivative. These four functions are useful. And for the diff function, for differences and approximate derivatives, the input is one-dimensional vector of length n, and output is the vector of length n minus 1 for the diff function. These can be used later to determine finite difference approximations of first derivative. So this diff only gives the differences. And let's, for example, when we write fx equals gradient f for this function, it gives numerical gradient, so numerical differentiation. And f, a one-dimensional vector of length n, this one, and fx here, a vector of length n containing differences based on f. So the first value returned is the difference between the first and second value. However, for the intermediate values, a centered difference based on the adjacent values is returned. And diff I is fi plus 1 minus fi minus 1 divided by 2, for example. So when you use diff, it's just the difference divided by 2 of these. The last value then computed as the difference between the final two values. And therefore, the results correspond to using centered differences for all the intermediate values with forward and backward differences at the ends. And the spacing between points is assumed to be equal to 1, so you have to be careful on that. That's why this is 2 actually. If you remember, the centered difference is the 2 times h, and h is assumed to be 1. So get the values of these functions such that you will have a step size of 1. Or actually, the centered value is x, for instance, 0.5 to the left, 0.5 to the right, the difference will be 1. But in that case, h should be 0.5. This becomes 1. So it doesn't like that. It doesn't work like that. When you say equal 1, that means h is 1. Then from x value, from fi or xi, for fi plus 1, we need to have xi plus 1, which is x plus 1. And for I minus 1, we need xi minus 1, which is xi minus 1. So because this is 1, so h is 1. Then get these results, then get the differentiation. If the vector represents equal space data, the following version divides all the results by the interval and hence returns the actual values of the derivatives. When you use this gradient f and h, so here the default h is 1, but when you use h here, then you can decide which spacing between points you are using. You can change it to 0.5, 0.25 easily in this scenario. Let's use these in an example in the following slide. In this slide, we have this function, and from x equals 0 to 0.8, we want to have diff and gradient functions. We want to use these to take the derivative. And they compare the result with exact derivative. You know, when you take the derivative of this, the first derivative is this. Let's use the diff function first. For the diff function, let's define the function, this one, in MATLAB using this. Then generate an equal space data between 0 and 8 with an h value of 0.1 and calculate the y values as the fx. Use short format, and when you use diff function here, it actually determines the differences between adjacent terms. So we have x terms here and y functions for these. When you use diff x, it uses the differences of x's. Like all of them are actually 0.1, 0.1, because in here from 0 to 0.8 we increase the values with 0.1 values. With 0.1 increases, h is 0.1. Then let's do the same with diff y, and then we will get the differences between y's. Then the differences between y's will be divided by the differences between x's to perform the division of the y differences by the x difference. This is the centered difference actually. now here. And the results are these for each space or each spacing, each data. And when we use diff fx divided by 0.1, 0.1 is the h value, the step size, because we use that here. And this is an alternative to last row, this one, because we have an equal space data, you can see here. Just use 0.1 instead of using this vector. When you use equal space data, you can simply use h here for division. Let's use gradient function as well. When you use gradient with 0.1 spacing for the y functions, it will give us similar results you can see here, but a little bit different. And when we plot the derivative estimates of the numerical approximations that we obtained in the previous slide, let's have the xi and yi, and these are the vectors to be able to generate, and these are the midpoints of x values. You can get midpoints to plot them. Let's plot them using this subplot with xi, yi are the analytical values. This is the analytical derivative to get the results, and this is the numerical ones with exam. So let's compare them. So you can see with the diff function we obtained very accurate results actually on the function. You can see the dots are the numerical values that we obtained in the previous slide, while this continuous line is from the actual derivative. Let's use the same for the gradient data instead of diff. When we have it, you can see, if you remember, there were some differences in the gradient function, and those differences show variations from the actual analytical data actually. So you can see that the diff function, when you use that for finite difference, it provides a better approximation compared to the gradient function. So gradient is using maybe forward difference, but with diff function we are using finite center difference. So center difference is more accurate. That's why we are getting a more accurate result over here. So you can simply try this in MATLAB and see how it works, and you can try different functions as well to be able to have some experience on the differentiation, numerical differentiation in MATLAB. And with this we finished chapter 23. You can read chapter 23 in your book to have further information about the numerical differentiation. Also, there is chapter 24, and it has some case studies related to the engineering area for numerical integration and differentiation, and you can read and see the examples over there as well to have some further understanding. Thank you very much for listening, and this is the end of chapter 23.